started talking about corrosion of metals, and the idea was to complement, we've been talking about mechanical properties quite a bit, and how to specify mechanical properties, how to specify the chemistry. When you do the material selection and the specification, sometimes you do want to have what we call corrosion control. And the idea with corrosion control is metals, they want to oxidize. And you generally don't completely prevent it. You want to control it. So the purpose of zinc is not to have zero reaction with the environment, but to limit it. We didn't talk too much about the effect, but for a hot dip galvanized piece that's exposed to the weather, like a bridge component, you can expect about 50 years life out of the hot dip galvanized coating. And so if you have the very thin layer one that's about 1/10 of the thickness, well, you're thinking about 4 or 5 years. Now, it could be as little as a year if you have salts and a lot of moisture. So that happens sometimes in tunnels. So people say that use galvanized components to put things together here. But after a year or two, it starts rusting, and then you know you're going to lose thickness very quickly. So it's just about being clear on your specification. We talked a little bit about issues of galvanic, and I said very briefly that it's an electrical connection and a liquid connection, which means the easiest thing to do sometimes is if you have two pieces of pipe, for example, in an assembly, or two beams that are not compatible and you want to put them together, you need to put a washer, a dielectric washer, and washers for the fastener that go through it as well, and you can isolate. You have sleeves and you have these washers. You can isolate electrically, and when you do that, it doesn't matter how close the two components are, because electrically they're not connected, so you can't have the galvanic effect. We talked about stainless, that it's very susceptible to chlorides for pitting, but also for stress corrosion, and that's a discussion we just had about using metals for deep water application where you want to prevent rust. If you go to a stainless, and it turns out you start having stress corrosion crack in the deep sea, that's not good. So you want to optimize your material selection to not have that risk. The good thing with environmental effects is a lot of times it's a go or no go. For aluminum, for example, one thing I say a lot is there's this zone of stability where the aluminum oxide will be on the surface. But if you have a very acidic environment, so a pH of 3 or less, you don't have that stable film on the surface, so you're going to corrode very quickly. And the same thing about a pH of 9 or 10. So sometimes if you have aluminum embedded in concrete, for example, it's a no-go if really you get the pH of the concrete of at around 12. You can have a very fast corrosion there, and you wouldn't expect it, but it's a problem that happens. So it's all, the effect of the environment is just very important, and there's only so much, of course, that we can go into the details. Yes?
So the metal oxides are always brittle. Like what makes, yeah, I guess, are they just always brittle?
The question was about the metal oxides, whether they are brittle or not. Yes, I mean, they all either intermetallics or just really oxides. And they can be porous, like when we put a clad treatment on the aluminum, we build up the aluminum oxide, but in a porous form, so it's not solid. And that's actually an advantage because you have more flexibility for when you apply the load, so things don't break and spall. So essentially, the main way that you avoid the brittleness and the spalling of the oxide under loads is to have a little bit of a porous structure. because otherwise you always have something that's a lot stiffer on the surface that will tend to break. And that's actually what happens in stress corrosion cracking. So if you have the tip of a crack on a piece of stainless, so we're really looking now inside the part. Let's say it's a relatively deep crack. So over here, you will try to protect the bare steel with an oxide, but there's so much load that it just tends to break and reform all the time. And it's depending on the chemistry, the amount of chloride you have and the temperature defines whether or not you're going to form something that's going to be stable. So the oxide stability on the surface is very important, but it's not just mechanical. It's part of whether it becomes very robust against diffusion. So you can form some oxide on steel, like a blackening treatment, that will reduce the rate of penetration of moisture and oxygen. So you really are slowing down your corrosion rate, or you have the more regular red rust that really is not helping at all because it's sufficiently porous that you have the chemicals, the water and salt going all the way to the interface, and keeps your corrosion rate very high. One thing that I tend to mention when we deal more and talk more about corrosion is you can have a very fixed rate. So if you submerge steel in water that's oxygenated, it's 4,000th of an inch per year. So 100 microns. It's very significant if you keep supplying the oxygen. So you can, whenever you make a calculation or estimate as to whether you worry that you're going to lose too much thickness, you can use that as a reference. If it's an application in the weather, you say it's moist 10% of the time, then now all of a sudden you only have 10 micrometer per year that you lose. So it's just, I think what it is you become more and more comfortable thinking of the consequences of corrosion when you can kind of quantify it. So in a soil, for example, if you bury a structure like piles for buildings, we know they won't lose more than 2,000th of an inch per year, so 50 micrometers. And what that means a lot of times is you do want to protect them. It's unfortunate because it's adding complexity a lot to a construction. But if you just use a sacrificial way, then after 50 years, you don't have a strong foundation to your building anymore. Yes?
Sorry, so two questions. So steel loses 2,000ths of an inch to corrosion per year. So what was that ballpark number?
Yeah, okay. So we were talking about corrosion in the soil. Is essentially less than in water. In water, we said about 4,000th of an inch. So in soil, it's approximately 2,000th of an inch. It could be significantly less if you have a dry environment, of course. But it's sort of a starting point. It could be a little more if you're really moist and if you're close to the water table, for example. But I think the bottom line is if you're thinking really, really long term, you probably all know about the first Church of Christ scientists at Mass Ave, the very elaborate building. When they were working to replace their wood piles in there, they said, I want 200 years. I don't want to have to go back, which is very unusual for somebody to be thinking that much long term. And as soon as essentially somebody says, I want more than 50 years, you need to protect the steel. You can't just think you're going to put that much more. And the reason is there's always going to be one area that's going to corrode more than another after a while. So just trying to work on the thickness was not reasonable. So it's not super common for buildings, but essentially that one building, we had a relatively elaborate cathodic protection system for underground condition. Now, when I say unusual for a building, it's very, very common for pipelines. We talked a little bit about pipelines yesterday, and most of the large ones do have the catalytic protection. A lot of the distribution lines don't, and that's part of the issue of replacement and wanting to go to plastics. Yes?
So if I had like a brick of 100% rust, and I like put it, and I did like a tensile test on it, so it sounds like it would be porous, and like how, yeah, like what would it?
Oh, are we talking about corrosion, or are we just now deciding to switch and talk about soil foundations? I think that maybe the way that I'll answer it is when you talk about a corrosion in the soil, you have moisture. That's a very important parameter, and sometimes you can have microbial assisted corrosion that changes the condition, but a very little is associated with the content of the aggregate or the rock that you have in the ground. It's really more about the soft face. So if you have clay, that's a very, very different behavior than sand with water, or just a regular organic soil is where the main differences are. Where we worry the most is normally at the water table, so between soil that's saturated and soil that's aerated is where your highest corrosion rate is going to be. Okay, so just to make sure we close the loop, if you remember when we were talking about material selection, we did talk about plastics. We had one specific lecture on plastics, and I want to relate here a little bit more just in the context of using plastics for a long-term application. We talked about doing some creep testing and knowing what happens in the long term. So now that we just talked about corrosion, it also happens in plastics, and I've alluded to it. I actually have some of these types of connectors. So if you have plastic pipes in your home, they'll come out of a roll like this, and then you have an expansion tool that increases the inside diameter of the pipe. You can slide these fittings in, and they have barbs, so just by viscoelasticity, it contracts back, and you have a joint. So there's very few ways to screw that up in the installation. I mean, you could potentially not insert it completely, not make the cut right, but it's a relatively easy process and quick process to do. They have tools to put it together. This one is assembled, so you'll see it has that barb feature on the inside, and you can see that the diameter is still a little bigger. So very, very attractive in the context of trying to put plumbing into a home that will supply the faucet, the shower, and everything that you can possibly think of. Now, it's only good if the plastic can continue to service over time, and the fittings. Now, these systems have been around in Europe for a little longer than in the US. In the US, there's been some issues related to the fittings sometimes, and some issues sometimes related to the plastic. So we'll talk about the plastic a little bit. There was a project I worked on where it wasn't just a piece of plastic. It actually had a little aluminum layer in the center. So, and the idea there was to be able to form the pipe. If you take this one and try to bend it, it's going to bend back. It wants to keep straight. And one advantage of these systems is you don't have to make that many joints. It's a little bit like wiring a home. So you can go from the faucet and turn into the walls, into the floor space, and not having to put an elbow each time. I mean, there will be conditions you do have to put joints, but a lot of times you'll turn without having to put a joint. So you save additional time on that. Now, again, if you make a bend in the pipe and it bounces back, it's not great. So people like the idea of having an aluminum layer in between. So you see the composite image on top. It's got plastic on the inside. It's got an aluminum layer and plastic on the outside. And that's all made by a single step extrusion process. So not expensive to do. The problem that happened there is people designed the system initially for radiant heat. So to put all the piping system under the floor and have continuous circulation with a boiler. In those conditions, you don't really have oxygen after a while because it's a closed loop system. You keep recirculating the same water in a heating system. Otherwise, you'll damage also your heating system itself. It's made out of cast iron and steel. It doesn't like too much the oxygen. So the purpose of the aluminum was to actually block penetration of oxygen from the home into the plumbing system to protect all the heating elements. And people started to realize, oh, I could use it for potable water as well because it's easier to work with. I can make these shapes. I don't need to put as many clamps to hold pieces in place. So there was a drive to start using it for potable water, but the polyethylene itself wasn't built with enough antioxidant to resist the oxygen of the potable water. So they had a lot of blistering like you see here, and as part of their failure analysis is you see the blister on the outside and you start thinking, well, so okay, what's going on? You find out that the aluminum corroded, and that's not really to be expected. It's not fun. I mean, it's a relatively thin sheet of aluminum that's bent over and then electroresistance welded. So of course the electroresistance is not always perfect. There may be some pat there for the moisture to flow, but upon more detailed review, essentially we found that the corrosion of the aluminum was because the pH fell below 3. And the reason why the pH fell below 3 in this case was the complete deterioration of the inner layer. And what I mean by complete deterioration is you have the polyethylene, you put antioxidant in it, and it doesn't react until you completely eliminate those antioxidants. So it's a little bit like wine that turns vinegar. It's all good until you reach a certain point where now you're turning over, there's no protection anymore, and you really start degrading. So it's unfortunate. It was, relatively consequential to a lot of installations. Of course, it depends on the use. If you have used more of that water, you have more problem over time. But in the context of the class, I think that essentially it was learning from mistakes. People realize, oh, I can't do that. So now, if you want to have those pipes for potable water, you need to spend more on the oxidation resistance of the resin. The composite that we've talked about in terms of mechanical properties, we said you get all that winding reinforcement to support the pipe from internal pressure. So it's all great. And I remember mentioning briefly one of the issue is moisture penetration, and the sample I brought in had this little thin layer on the outside to prevent moisture from getting to the structural wall. So you see here on a long-term service, and for these composites, a lot of time we'll do a cyclic load, a fatigue test, just to mimic what happens in creep, so in just long-term loading. And what it says is the proportion of time that is involved in debonding versus cracking, they kind of merge here. So when you are looking at a relatively long life, the time for losing the bond between your reinforcement and your matrix defines the life, essentially. So if you can extend over here, if you can extend that line by preventing moisture penetration and the debonding, that's how you extend your life. It doesn't show up on the short term. So these are all when in the context of including composites in aircraft fuselage, that's a big consideration. People need to be thinking in 10, 15 years, if this aircraft is going to be in a moist environment, am I going to have the bonding of interfaces? And it's becoming really what governs the long-term life. If you can keep it dry, it's great.
So does cycles relate to how moisture dry is?
Well, I'm really just using this to emphasize the importance of not losing the bond on a composite. And so if you can engineer it so it doesn't debond by moisture penetration, you know you'll have a much longer life. Yes, thank you. So we'll switch and talk a little bit about joining. And I only want to go very briefly to two examples. One is just a socket joint for copper. By the way, that's still used very much, because it doesn't degrade in ways that other materials would, so it's still considered, I guess, the gold standard. So you make a joint by putting the two pieces, so the plain pipe into a socket is the typical way, so it's essentially a lap joint. And I brought one in that was done and then pulled apart. Let's make sure, yep. So the two pieces fit this way. It's just about 1/3 of the full circumference here that we're looking at. That was essentially flattened up and pulled apart. And what you'll see is the solder material that was fused and essentially inserted the joint by capillarity. And there will be a few spots where it's shiny. When it's shiny, it means you didn't have a bond, and therefore there was a path for the water to penetrate. And when it's dull is where you had the bonding. And there will be a few spots that you just absolutely have nothing. So this one does correspond with this one here, just like that. There's a little line with 9 degrees if you want to reorient things. And even though you want to do a good surface preparation, so over here, you'll see that the pipe was sanded to remove the oxide. You put a flux, you heat up, and then you bring your filler metal. The practice of things is sometimes you don't have the easiest access. Sometimes the heat is not always going to be the same. So the idea that you get a full joint penetration all the time, like the entire space between the two pieces being filled, is not likely. There's always going to be some form of porosity. And then the question for the industry is, what is acceptable? Well, it turns out that in this case, the ASTM standard tells you how to do it. So it's an unfortunate example. Standard practice for making a joint. You measure, you ream, you clean, you flux, you assemble, you heat, you apply, you cool, and you clean. That's it. So it's one example where if you say, for example, the Copper Development Association arrived to a criteria, they said you want at least 70% of the joint that's filled. It's not unreasonable, you know, it's kind of a passing grade. But this requirement is not an ASTM, so it just points to this idea when you specify material and process, what exactly do you want? You can't get 100%. If you want prime quality, I mean, I could ask for 80% if I want to, and then like the only way you know whether you got it is you can do some X-ray of these and find out that's okay for quality procedure development and to qualify the welders, the plumbers. In the practice of things, you don't normally want to do that. You can peel it off like we did, which for procedure verification and the plumber qualification is more practical. You don't need to send it out. You really have them do it, and then you take it apart. So this one's good. This one's not good. You try to do it too quick because it tends to be harder on the bigger pipes because you need to wait longer for everything to heat up before you start bringing on the metal.
The flux data?
Flux, very important, yes.
What is that?
It's really organic. It picks up. It's just like a low temperature slag. So it's an ionic liquid that picks up all the oxide on the surface to get you a clean surface of metal to bond with the other metal.
Okay, so it is literally a weld then, basically.
It's well, okay. So it's not fusion welding because you clean the copper, and you bring a liquid metal into the joint by capillarity. So it gets drawn because it's a very confined space. So you're reducing the amount of free surfaces, and it only works if really you're replacing two metal interfaces with just one. But if you're trying to put the metal in an oxide, it doesn't reduce the energy, so it doesn't want to do it. Yeah, and a lot of times you can tell when you have the filler metal whether it's getting into the joint or not. And that's a way that the experienced plumber is like, oh, I know I have a problem. I should just take it off and do it again, type of thing. Because the good thing with this is if you heat it up enough, you can take the joint apart again. So that's an advantage when you know you had the problem. The fusion welding, which is more what we've been talking about during the class, goes under different standards that you can call for. So you can call for an API standard. There are some ASME standards for pressure vessels. I'm bringing up the AWS D1.1. I spent about 3 lectures in the fall on this, and I will next fall. But the idea there is essentially one code. It's about 300 pages, goes over design of a fusion welded joint. So if you have a fillet, if you have a groove, it will tell you how to think about it in terms even of a factor of safety. It will tell you how to qualify the welder, how to qualify your procedure, how to make the joint, and how to inspect it. Now, this code will ask only for a visual inspection of the weld. So if you are interested in using more advanced non-destructive testing technique, you have to add that to your specification. Because when you just say, do everything by AWS, by default, it does not include anything more than visually looking at the weld after it was done. So it's a little limited. Okay, so we'll go on an example that involves both corrosion and welding. It's an investigation of a large cable crane that was used to build a bypass bridge for the Hoover Dam. You can see it with the big lights. So here you have 2 towers, and you have another 2 tower on this side, and you see the sagging cable. You actually see the big trolley here. So this system worked with the 2 towers on each side of the canyon, tilting a little bit back and forth to position everything that you wanted to supply for the construction of that arch. So 50-ton pieces of post-tension concrete that were just lowered one at a time to make the installation. So it required detailed positioning. You have to resist wind and kind of all sorts of dynamic that are possible in the process. They were not really approved to do it, but they would carry some of the workers also back and forth. And you can argue it 2 ways. You could say, well, it didn't have the necessary factor of safety to do that. But then you think the other way, the other option, practical option, was to have the workers crawl up the arch each time. So, which one is more dangerous? I guess it's to be determined. So what happened is they did have a storm, and they shut down the construction site, and the cranes collapsed. So this is just a little more detail on how they look like, and you'll have that set. The 4 towers are underground. You have, I don't know, maybe 300 connections broken, 500. I didn't add them all up. So one of the first order priority was trying to see which tower fell first. It wasn't an issue with the main cables. All the cables were okay, except for one, but we'll skip that part for today. One tower crumbled on itself. So that was, a different behavior than just completely being pulled over by, a lack of stability of the other guys. So without going into the details of the other one, let's say we focus on that one right now and start looking at the details of how the joints broke. And this is a little cluttered, but I want to just bring it up just as an example of something you can do. If you're looking at this height, for example, right over here, there was a lot of opening of the entire 4-leg system. So the tower was essentially angles at each corner and diagonals on all the faces. And it's this point where it just grew in diameter. So it's a potential site for failing in tension, just like that. Or it could be that it failed in tension after another section of it shear. But it's just this kind of, I guess, lack of internal strength of this one tower. So what happened to it in terms of it failing? There was a lot of connections that were done this way, and I brought this in to try to help. So if you have different tubes, we use tubes for buckling resistance, and it's relatively inexpensive as well. So we want to use these tubes as diagonals, and you have to connect them to the main member. So the easiest way is to have this notch, and you put a plate in between. That's called a gusset plate to make these connections. We can see some of those if we look back here. So you have a main tube on the vertical, and you'll see those sometimes. It's very important to have them when you have cyclic loading. But if it's a building, if you go to an airport, sometimes you will see the main beams just welded together. It looks better. But this is a more performant way to use the metal because these welded joints are loaded in shear as opposed to being in straight tension. So it's really, really different. Now, the people that put that segment of crane together didn't really understand all of it because they welded here the section that was in shear, but they also welded the top that's completely transverse to the weld. So they lost that ability to have a greater resistant and cyclic loading for the shear mode by just adding too much metal. There wasn't any good reason to do it because the ends of the tubes were open anyway. Sometimes you will do that to be sealed, like on a bicycle. You'll really go all around everything to make it solid. But in this case, essentially, this idea of putting a welded bead all around the interface lowered the capacity by about a factor of 3. And this is schematic here. It's a little loaded, of course. We have the amplitude of the stress and then the time it takes to fail. And what you see is different lines here for different geometries of welded joints. If you don't have a weld, that's a category A here. It's a very, very high strength. But as you go into a joint that's even loaded primary and shear, you become into these category B, C, D. And the one that has the weld perpendicular to the direction you load is typically a category E. So E here you are at only 5 KSI as opposed to 20, 25 KSI for plain joints. It's very, very large reduction in strength. For aluminum, can be as low as 2 KSI. So 5 to 10% of the static strength is all you get in cyclic loading when you have the joint welded perpendicular. Yes?
So they should have welded it just on the sides, not like the rounded.
That's right. So not the part that cracked right here. So over here we're looking, we have the gusset going on. This is the notch. So you want to make the notch bigger and not fill it in with a filler metal. So you should have stopped right here and right there, because what happened here, it started to crack right there in the tension zone where the loading is this way, it was perpendicular, and then of course it started to propagate in different directions. It wasn't the only issue. When they refurbished the crane, you can see some corrosion on the inside of the tube that was painted after the fact. So this is reality. I'm not making anything up. So it was heavily pitted. You see the roughness, and you see the paint over the roughness. So you knew you had a significant thickness reduction. And as any atmospheric corrosion goes, that thickness was not the same everywhere. So it does add to essentially make this connection really not as good as it was in the first place. And on the first place, it wasn't very resistant to cyclic load because of welding the tension part of the connection. And you can see it here. So here we're looking at the tube this way that cracked right starting at this location and went all around. And this was very old. This crack pre-existed. There were some parts that you could actually see paint into the crack. Yes?
I know this is not the correct way to paint this or maintain a coat. What kind of protection does painting offer materials?
It's a very good question.
If any other.
It will prevent the loss of thickness for as long as it's adhering. So the problem with a protective coating, an organic protective coating, is over time you'll have moisture penetration through it, and that starts the corrosion reaction and starts to, you lose the bond of the coating against the metal. If you use a very high quality epoxy preparation and something that's essentially very resistant to moisture, you can go to 20 years just with an organic coating, but you can't have scratch on that coating, and it needs to be put on very carefully on the first place.
You might have another coating like a galvanized coating.
You can do that, yes. So the question was about combining organic coating with galvanizing. And it is now used for a lot of bridge constructions, for example, but there's a lot of care to get the organic coating to bond to galvanizing. If you essentially soak the structural steel in liquid zinc, it will take a while to degas. So just all these reactions don't help. So what I've seen people do locally here, there's a shop that does this day in, day out. They mechanically grind the surface of the galvanizing to get a good bond for the organic coating. And you can essentially have a two-level protection. The first protection is, it looks great, it's painted, and then when you lose that, you still have a galvanizing to rely on. Yes?
So you said the metal was already rusted and pitted, and then they painted over it.
Yes, they did that, and it was just not good repair procedure. Essentially, on this example, the people that prepared the crane for reservice didn't really have enough guideline on evaluating it first. Both in terms of the design and the deterioration. So it's very unfortunate.
So let's say you have a rod and someone paints it. After a while, it could never, assuming if all the paint was still on it, it would never like internally hit and look bumpy like that. Like if you see
Yeah.
that it's bumpy and they painted it, that means it was already like that, and then they painted over it.
Yeah, so the question was about getting corrosion under the coating. If you have that, you can't keep the bond. If you're building it, because, that's one thing that I did want to mention. Well, when you form rust on steel, it grows. And we're not talking about a small amount. Your density or volume goes up 2 or 3 times. So you have to put that material somewhere. And it's a problem for a bolted connection or a riveted connection. We call it packed rust. It's super strong, and it essentially can grow and deform rivets to the point of breaking them. So you do want to avoid corrosion in interfaces. We'll touch on factors of safety. We'll have to finish it on Friday, which is perfectly fine. I've covered a little bit of it in the sense that I think you guys realize you design something and then a lot of things happens to it. It's not being used for the way that you thought it would be used. It was refurbished, but not completely. People didn't think about cyclic loading, because the main reason we have this issue with the gusset plates, the load varies up and down. If it's a one-time loading, it's okay. So if we talk about the dead weight of a building, then people don't worry about it as much. So the factor of safety, you have 2 ways that people quantify it. One is the failure load divided by the allowable load. I like that one because it's very easy to quantify, and it's typically a lower number. So you take the assembly and you know what it's going to break at, and then you know what the rating is. So if you have a chain that is, say, going to be good for 1,000 pounds, and so that's the rating that you put on it, and then you decide that when you pull on it, you want it to hold for 2,000 pounds. So you have a factor of safety of 2. If it's OSHA, you will need a factor of 4 or 5, just the way it is. The other definition, so the N value there that's used for pressure vessel and a lot of pipelines, they use the yield stress divided by the working stress. So the issue there with working stress is it can be exceeded. So if you have a liquid transportation system that the maximum allowable service pressure is, say, 100 psi, just as an example. So you have 100 psi, that's what you normally use. Now, if you shut a valve very quickly, or if something happens, you have essentially a steam, and then you start having some liquid, and there's some dynamic effect with water hammers, there will be extra loads. So the way the pressure vessel and some of the pipe design people think of this is, we don't really know how higher these stresses are, so we will just build into the safety factor. So when you go into these pressure vessels, you have a lot bigger factor of safety. And it's not because that they overbuilt with respect to the pressure vessel. It's mostly because they don't account for the worst case loads when they establish that factor of safety. On the OSHA, when we're talking about a factor of safety of 4, that's different, because the OSHA is the first criteria here, failure load divided by allowable load. So it is built in with an actual greater factor of safety than the pressure vessel. So all I'm trying to do is emphasize that the number for the factor of safety doesn't tell you the whole story. It really depends how you determine that number. So for a big civil infrastructure, the New Orleans levee, when they let go, the design factor of safety was only 1.3. Now, what does that mean is they assume a certain elevation of the water based on the height of the levee. It gets all the way to the top. Certain soil properties that were a little conservative, and because of the size of the structure and the fact that you can only get so much water, they didn't take necessarily of the wave effect and all that. They said factor safety 1.3. That's all I'm going to pay for, because otherwise I have to bring in a lot more reinforcement for this levee. So it didn't work. And a part of the issue moving forward is when these things affect a lot of people is also when you do want to raise your reliability. So they've been through a lot of processes to improve both their understanding of the loads being applied and the estimate of the capacity for soils that are getting infiltrated and filled with water, so you have less shear resistance and all that. An aircraft will have also a relatively low number for the factor of safety, for the reason that everything is analyzed and specified fairly precisely. For landing gears, it could be just 15%. So 1.15 is your factor of safety, because you really do take the worst case loading scenario that you can arrive to, and then the lowest material capacity from all the processing specifications. You know you're not using any casting, so you know very well your strength. So that really is helping a lot with that. So when we think about factor of safety, we have, again, to be very, very careful. Does it include everything? So by including everything, you have the use, you have maintenance. So am I going to assume that my steel is never going to lose thickness? In other words, when I start having corrosion, somebody's going to come and repair it? That's an assumption. Is it going to be used for other purposes that I did not anticipate, and what are the consequences of that? So to some extent, in a general application, the demand may be as hard, if not harder, to determine. On the capacity, you have a lot of things: design, specification, how it's built, how it's inspected. So that was the example, for example, of the copper pipe and welding, what exactly you're trying to do. So it's a lot of variables, but to some extent, if you're careful, I think you can control the capacity side a little better sometimes. And what it boils down to is if you have an overload, and that happens, I have cases like come along, for example. You just have this big jack or structure that's used for a certain capacity to lift a car, pull a car, or do any significant transfer of load. The idea is you try to get these things to break in a way that they don't shatter. So if I'm overloading something that I built, I want the handle to let go. I want everything to buckle instead of having a snap that leads to a dynamic release. The hook goes and something like that, and that's not really cool. So I think what I'm saying is the idea to deal with abuse and misuse, even for landing gear, if it's going to crumble a little bit, that's a lot better than if the wheel goes flying. Because at least you made that one shot, and you know you can't fly again because you can't put it back. So, and it's very, very true of a lot of structure. Like we talk about aircrafts. If you really go through a huge storm, you want the aircraft to be able to land, but being all mangled, you can't use it again. So the wings are now a foot lower than they were at the beginning, but they didn't break up in the air, is what we're going through. So we'll continue on Friday and go over the fracture surface. Thank you.